Assalamualaikum and hi everyone. This is the second part of a three-series video lecture on Chapter 3 Vector Valued Function. In this video, I will teach you on the subtopic of 3.3 arc length, unit tangent vector, principal unit normal vector, and curvature. In this subtopic, there are five items that will be covered. The arc length of a smooth curve, the arc length parameter with base point, unit tangent vector, principal unit normal vector, and finally the curvature. So let's take a look on the first item of this subtopic. Okay, first we're going to learn about arc length of a smooth curve. The arc length L of a smooth curve vector function ft, which the t range from a to b, that is traced exactly once as t increases from t equals to a to t equals to b, can be defined as this equation given here. So you can see that you need to integrate from the limit of constant a to constant b. Then we will going to do a square root of the components of the derivative of the vector function ft. So you need to put the derivative component x1 squared plus derivative component y1 squared plus derivative component z1 squared. Then you need to solve the integration. Yes, you have, as I have mentioned before, there are two types of arc length. So you might be wondering, so when will I use this equation? So to use this equation, you have to look at the limit of the given question. If the limit of the vector function is given as constant value, then you're going to use this equation. In some questions, you may notice that they will not use the term arc length, but they're going to use the term of length of the curve. Both of them are the same. To get a better understanding, let us try example 1. Find the length of the curve vector function rt given as sin t minus cos ti plus cos t plus sin tj from t equals to 0 to t equals to pi. So to decide which equation that we're going to use, look at the limit that is given for t. You can see that the limit is given from 0 to pi. Both are constant values. So you're going to use the equation that I just introduced you just now, which is this equation. So we need to find the derivative for the vector function rt. So for the first component, which is sin t minus cos t, so we have the equation here. We need to differentiate it so that we will get the derivative of x1, which is given as x1 prime t is equals to cos t plus sin t. Next, we're going to find the derivative for the component of y1 and z1, which is given as, so we have here the equation for the component y1. Then the derivative can be defined as negative sin t plus cos t. Looking at the vector function, we only have the component for I and j. So then we can just ignore for the z component. We already have all the derivative component to be put inside the square root. So we're going to solve for the length now. As mentioned before, because we have the limit in both of the upper and lower limit of the integration, t is both of them are values, so we're going to use this equation. Putting all the derivative component that we have done previously, then you will get this one. So you will get the integration from 0 to pi, and you do a square root of cos t plus sin t squared plus negative sin t plus cos t squared. Then you're going to integrate with respect to t. What we can do to solve this integration is we expand the equation, then we will get the longer version of the component. So from here, after we make simplify the equation, you will get the component in a much simpler form given as 2 cos squared t plus 2 sine squared t. This can be simplified by using the trigonometric identity of cos squared t plus sine squared t equals to 1. So then we can simplify this into just square root of 2. Then we can just simply solve this one to get square root of 2 times t, where we have the limit at 0 until pi, and then we put it into our equation of square root 2 times t, we will get square root 2 pi. And that's the final answer for example 1. Next, we're going to take a look at another type of arc length, which when we were given a base point. The arc length parameter as a function of t of a smooth curve, the vector function ft, that is traced from t equals to t naught to any value of t is given as this equation. So for this equation, you can notice that the limit for TO, it might be t is normally a function of t. It's a function, and this can be a function or it can be a value or both. So it can be either function or value. So when we want to use this equation, we use this equation when the question gives you the limit of the length as a function of t. To get a better understanding, so let's us try example 2. Find the arc length parameter along the curve R as a vector R, which is given as 4 cos ti plus 4 sin tj plus 3 tk from the point where t equals to 0. Then find the length of the curve within the interval t must be bigger or equals to 0 and t must be smaller and equals to pi over 2. For this question, you can either use the first equation that I have shown you in the initial of this video, but we're going to use the second equation, which is the arc length parameter with base point. The information given is that the minimum integration limit is given as t naught equals to 0. And as for the maximum integration limit, because the information is not given in the question, so we can assume that t must be bigger than 0. So we're going to use this equation. If you look at the equation, you notice that we still need to find the derivative for the component of our vector curve. So we're going to do that first. So for the component of x1 t, we got 4 cos t. So if we differentiate it, we will get negative 4 sin t. Next, we're going to do the second component of y1. y1 is given as 4 sin t. If we differentiate 4 sin t, then we will get 4 cos t. And finally, we're going to solve for z component. z1 is given as 3t. So if we differentiate 3t, we will get just the constant 3. So now we can just plug in the derivative of this component into our equation. So after we plug in all this value, we will get something like this, which then we're going to expand the equation. You will obtain 16 sine squared delta plus 16 cos squared delta plus 9. Using the trigonometric identity of sine squared t plus cos squared t equals to 1. So we're going to plug in this identity into this equation. We will get this one. Now it is much more simplified. The argument for your integration only consists of a constant, which is the square root of 16 plus 9. So if you solve it, then you get a square root of 25, which is equal. So then if we integrate 5, we will get, we integrate it with respect to delta, we will get 5 delta, with our limit is between 0 to t. So if we solve this, then we will get 5t. So the equation for the arc length parameter, you will get the equation for the arc length parameter along the curve of the vector function rt, you will get the equation as 5t. But now the question also mentioned to find the length of the curve within the interval of 0 to pi over 2. So we are going to plug in this value into our equation of 5t. We can write down the length as equals to 5t. So if our t is equals to pi over 2, then the length will be equal to 5 pi over 2. And that's the final answer for example 2. The next item in this video is the unit tangent vector. So the unit tangent vector, the symbol is bold capital letter T of a smooth curve. The vector function of ft is given as the derivative of ft divided by the magnitude of ft. So how do we get how we determine the magnitude of ft? You can use this equation to find the magnitude for the derivative of ft. So you just have to differentiate ft, then take the component. Each component have to be squared. Then after that, you square root all of them. Then you will get the magnitude of f prime t. Okay, so this is the equation for unit vector function. Next, we're going to take a look at principal unit normal vector. The principal unit normal vector, which the symbol given as bold capital letter N, of the smooth curve, our vector function ft can be calculated by using the definition of the derivative of our tangent divided by the magnitude of our derivative of tangent. So to get this one, if our unit tangent vector is given as x to ti plus y to tj plus z to tk, then the magnitude of the derivative of tangent is given as this equation. To understand about the unit tangent vector and also the principal unit normal vector, we're going to try example 3. Find the principal unit normal vector for the vector function rt equals to ti plus 3 sin tj plus 3 cos tk. So for unit normal vector, the equation is given as the derivative of tangent divided by the magnitude of the derivative of tangent. So we need to find our tangent vector. To find the tangent vector, you need to use this equation, which is given as the derivative of our vector function divided by the magnitude of the derivative of the vector function. So we need to differentiate our vector function first. So if you differentiate rt, you will get I plus 3 cos tj minus 3 sin tk. Next, we're going to find the magnitude of r prime t, which is given as the square root of 1 squared plus 3 cos t squared plus negative 3 sin t squared. So we need to expand the component in the bracket, and the square root will turn into something like this: 1 plus 9 cos squared t plus 9 sin squared t. Again, using the trigonometric identity of cos squared t plus sin squared t equals to 1, which is given as cos squared t plus sin squared t equals to 1. So this we can plug in into this equation, and it can be simplified into the square root of 1 plus 9. That can be solved as the square root of 10, which is the magnitude for the derivative of our vector function. Using the value that we had obtained just now, so we now have the derivative of r, which is in a vector function, divided by the magnitude of our derivative of r prime, given as square root of 10. So this is the tangent vector, this one. As we already have the value of our tangent, now we can move on to find the derivative of t prime, so that we can find the principal unit normal vector. By differentiation, by finding the derivative of our tangent, we will get negative 3 sine tj minus 3 cos tk divided by square root of 10. Next, we need to find the magnitude of the derivative of tangent. You will obtain something like this. We're going to expand the component so that we will turn in the square root of 9 sine squared t plus 9 cos squared t divided by 10. We're going to use the trigonometric identity of cos squared t plus sine squared t equals to 1, so that it will be simplified into the square root of 9 divided by 10, which can be simplified even more, and it will turn into 3 divided by square root of 10. Now we already have the component that we need to solve for our normal, the principal unit normal vector. So plug in the value for the vector function for the derivative of tangent vector, and also the magnitude for the derivative of tangent vector. You will get negative 3 sine tj minus 3 cos tk divided by 3, which can be simplified into negative sine tj minus cos tk. And that's how you solve example 3. The final item for this video lecture is curvature. So the curvature, which the symbol given is k-bull, of the smooth curve of vector function ft can be calculated by finding the magnitude of the derivative of tangent vector, and also the magnitude of the derivative of our vector function. So we're going to do example 4. Find the curvature of the straight line RT equals to TI plus 2TJ. So the equation for the curvature is given as this equation here. The magnitude of derivative of tangent divided by the magnitude of the derivative of FT. Using the symbol used in this equation, so we can change the equation in this one. So we substitute the derivative of f as the derivative of r. Next, we're going to find the derivative of r. So if you differentiate ti plus 2tj, you will get I plus 2j. The magnitude for the derivative of r is given as the square root of 1 squared plus 2 squared, which when solved, it will give you a square root of 5. We already have our derivative of r and its magnitude, so we're going to find the tangent vector. So the tangent vector is given as the derivative of r divided by the magnitude of the derivative of r. Plug in the value that we have obtained just now, so we'll get I plus 2j divided by square root of 5. If we differentiate the tangent vector, we will get 0, because all the components only involve constant value. If we find the magnitude of the derivative of tangent, we will also obtain a 0. So I write down back the equation for the curvature, the magnitude of the derivative of tangent divided by the magnitude of the derivative of r. So I plug in all the values, you will get 0 divided by the square root of 5, which eventually will give you a value of 0. So your curvature is given as 0. And that's how example 4 can be solved. That's all for this video. Thank you and have a nice day.